Okay, so you hear me? Yes, yes, okay. Okay, so I will start. We switch the program because York was not fully ready for his lecture, so he preferred to have his usual lecture at the beginning of the afternoon. So I will start with the all you want to know or not want to know about laser cooling. I am a poor note writer, so I rely on the lecture notes of Hélène Perrin, who gave the same lecture here a few years ago. And maybe in my notation, what she calls the detuning small delta has become a large delta, but this is just, I think that you will recognize it. So the field of laser cooling was born before you, as it was born in 1985 with theoretical ideas that were about already 1 decade in age. The first proposal being from the middle of the 70s. So this is the date for the first laser cooling system, and then 2 years later the first MOT has been demonstrated, and now the MOT is the basic tool. So the MOT is the magneto-optical trap, but probably all of you know. Yes, maybe a question. Have you ever seen a MOT working? Who didn't never saw a MOT working? Okay. No, I was not asking if you saw a MOT not working. I saw if you didn't see any MOT working. So there are, in fact, 3 theoreticians, pure theoreticians. No, it's not bad. Okay. I have in Lille we have made a MOT which is transportable, and but I didn't bring it here. It's just stand on the table like that, and it has a rack of electronics, and you just put it in a truck, and you just bring it anywhere. We went with it in Paris in the Palais de la Découverte a few years ago, and we showed there for everybody a MOT which is working. Okay, so this is not the point. Yes, so this is just the I would say that I almost stick on the lecture notes of Hélène. Jean Dalibard have written wonderful notes about the same subject. It is almost 150 pages, but it is in French, so if you read French, it is not a problem. Otherwise, the historical foundation, we would say, of cold atoms is in Les Houches 1990, where you can find the book in the library, probably. It should be there. And the lecture notes of Cohen Tanuji and Bill Phillips are the fundamentals of what you have to know. Okay, so I have 4 lectures, 3 in this week and 1 in the next week, and so I naturally divided my lecture in 4 pieces. So the first one, we will start with the simplest atom, which is a 2-level atom, and we will play with it and see what we can do with a 2-level atom, and we will end up with the light forces. Then after 2 come 3. And so we will go to the 3-level atom. And in this case, we will end up with the Mott and the Doppler cooling. And then it is not 4, it is simply more, because I don't know exactly how to count them. And so this leads to the sub-Doppler cooling, as Thierry has already pointed out on the thermometer. And the fourth lecture will be, let's say, beyond the simple Mott. And we will look at the Mott not simply just as single atoms that are manipulated with laser fields, but as a whole, where you have the atoms that see each other and make a shadow on the other, and so it becomes a nonlinear object with the dynamical properties that resembles those found in the plasma. So it is not a star in the cell, but you can see things, instabilities that resembles a lot with plasma physics. Okay, so let's start again. 2-level atoms. So you know that a 2-level atom is just a theoretical view or a theoretician's view of real life. And in fact, you never find 2-level atoms. So what is a 2-level atom? So in fact, in case of hydrogen, you know that you have the ground level, then you have a first excited, and then you have a series, and you end up with the ionization of your atom. And what does it mean in this mess of infinite number of levels? What does it mean to consider just a 2-level atom? So in fact, it is an approximation of the reality. And to understand what we want to point out, to figure out in this infinite number of levels, just figure out 2 levels of interest, you have to consider a problem. And the problem is that we just want to have an atom interacting with light and in the semi-classical limit. Okay. So you know that atoms are quantum objects. I have added this semi-classical limit or semi-classical approach to clearly state that some other approaches are possible, and probably we will see this later on. I don't know exactly when, but so now we just want to consider an atom plus a laser field. So you have your atom with several levels, and we turn on a monochromatic electric field. And so it has a characteristic, it has a frequency and only one frequency, which is called omega L for the laser. We also consider that the laser is intense enough so that you do not count the photon one by one, but you have plenty of them, 10 to the 10, 10 to the 15, 10 to the 20, so a lot of them. This is important because when you have many, many photons, then you can go to the classical description of the field, which means that with the complex notation you can write maybe just I don't 1/2 of E exponential minus E omega L T plus CC. Okay, so this is just the usual electric field. Obviously, this field can depend on position, so you can add here R, maybe, and you just consider that the amplitude of the field depends on the position, but its frequency does not depend on you have only a monochromatic field. So very often, so this is a complex vector, and so it is very often useful or sympathetic or better or whatever you want to introduce some real quantity instead of complex ones. And usually I write the amplitude of the field, which is just the amplitude of the field. And obviously this is not enough. You have to introduce also a phase of the field, and then you rewrite the first equation, this equation, or simply E, then you write the vector depending on the position, which is a polarization vector, which is still complex in some cases. If you can do it real, it's better. E of R and exponential minus phi of R. Okay, and so this one is real, and this one is real also. Okay, this is the laser. Now we have this atom and this field, and what we will consider a two-level atom is already the case where you have somewhere in this ladder of levels a pair of levels whose frequency is just omega 0, and something fantastic occurs when you have one frequency and only one frequency, which is on the order of the frequency omega L of the laser. And at this point, you will say that these two levels will play a special role, and all the other, you can forget them. And so we just want to check and to see exactly in which condition you can treat these two levels, forgetting everything else. Okay, so I start again drawing, and I put a name on the two levels because it is very useful to put names, because after that you can call them by their names. And so this is the frequency of the transition, and you can also have some decay. So usually we call this level the ground state, but it is not necessarily the ground state. You can, as I have drawn here, play somewhere in the excited states. Obviously, if what I call the ground state is in fact an excited state, then you have to work out a way to have some population in it as in a stationary regime, which is not a problem in the ground state, because if you do nothing, all the atoms just come back in the ground state. So just to fix some ideas, I will consider very often the cesium atom, and so the mass of the cesium atom is 2.2 10 to the minus 25 kilograms, which is the official unit. If we consider the D2 line on cesium, it has a frequency which is 2 pi. This is because it is a frequency, and it is in the hundreds of terahertz range, and the wavelength is 8075 nanometers. Yes, okay. You know that is. And the lifetime of the excited state is on the order of 30 nanoseconds, which means that the natural width is 2 pi 5.3 megahertz. So this is just preventive and to give you figures. Okay. If you just compute, for instance, yes, we just add it here, the thermal velocity at a temperature which is T in 1D for simplicity, it is just square root of kBT divided by m. And if you put the figures that are here, you find that for cesium it is 140 meters per second. And so this is for cesium. If you want to know for sodium, which is lighter, you find back again the usual speed of sound. And another quantity that will come back very often is the recoil velocity, which is in fact, if you have an atom at rest, when it will absorb one photon on resonance, you have an isolated system, so the momentum is conserved, and so the atom will have to move after the absorption with a velocity which is just the initial momentum of the photon. And if you want some figures, this is 3.5 millimeters per second for cesium, and it is, I think, for sodium, and much higher for helium, for instance. You have recoil velocities that are much higher. Okay, this is just to point out the fact that if you want to remove all the thermal velocity just with photons, you will have to exchange, you would make the ratio of these two, and if I trust my lecture notes, you need 40,000 photons to cool, to exchange the momentum due to thermal excitation. And if you just consider that you can exchange one photon each 2 tau, because you have the time to excite it, you have to wait the atom emits a spontaneous photon before you can excite it again. So it means that if you saturate your transition, it takes about a few milliseconds to take away all the energy. And if you want to know what is the acceleration, because you always think, if I were an atom, what should I feel? And you will feel very bad, because the acceleration is on the order of gamma times the recoil velocity, and it means that it is something in the meter per second squared. So it is 10,000 times the acceleration of gravity. And usually you do not accept this. Okay. In fact, these simple figures, I am cheating, just giving this to you, because we have the Doppler width, the Doppler effect, and this Doppler effect turns out, so it is just KL times the thermal velocity we have here, and it turns out to be on the order of 10 to the 9 radian per second, which means that it is much larger than gamma, and which means that when you decelerate your atom, you put it out of resonance, and so it is not so simple to exchange this large number of photons with it. Okay. Let's continue. Okay, for the moment I said nothing, and now I just take my cap of theoretician and I say, okay, what I need is the, no, this was like that, the Hamiltonian. Without any Hamiltonian you can do nothing. And so what is my Hamiltonian? So I have a two-level atom plus a laser field, a classical laser field, and plus, obviously, what you never get rid of, which is the quantum vacuum Okay. So if I write the Hamiltonian, I have H, which is the two-level atom, plus the coupling between the laser and the laser and the atom, plus the Hamiltonian of the vacuum field, plus the coupling between the atom and the vacuum field. Okay, so this part, in fact, we will introduce it as a quantum fluctuating field which induces the relaxation, and we drop it very quickly. And the reason is that here you have a lot of empty modes that are coupled to the atom, but it is a fluctuating part, and you will just we will introduce it as a relaxation term directly in the master equation in a few minutes, I hope. Okay, so let's start with the simplest part, so the atomic Hamiltonian. So you have, which is h bar omega 0, and it is just the projector on the excited state. I take the 0 of energy for the ground state. So this is the internal state of the atom, and obviously you have also the momentum operator p squared over 2m, which is the position. Obviously, so it is the momentum. You can guess that somewhere I will introduce also the r, which is the position operator for my atom. Okay. So this was the first part, the simplest one, and so now we just want to know the coupling between the atom and the laser. Okay, so in fact you can have a lot of couplings, and we pick up in this lecture the fact we will assume that the transition is a dipolar electric transition, so which means that you are simply, you have a dipole, an electrical dipole somewhere, and the interaction is minus d times E. So obviously, if you have an atom is a nucleus with some electrons that are orbiting around, and usually you do not have any dipole, electrical dipole in the atom. It is 0, but the field will induce this dipole moment, and so it is now this induced dipole moment that will interact with the field and gives you the energy. So we introduce the dipole operator for the atom as the coupling between the ground and the excited state, and obviously you have J E. So this is the reduced dipole element. So usually, so very often one writes the things the other way around. So it is the dipole, the reduced dipole, that is the dipolar operator taken between the ground and the excited level. Yes. Okay. So now we have our VEL that is minus D E. The field is classical because you have plenty of photons, so it is not an operator. But it depends on the position and time, and the dependence in position makes it an operator. Okay, so I am lucky, yes, I have still the expression of E here. So this was EL probably. And when you make it explicit, this turns out to be 1/2 of epsilon L of R EL of R exponential minus E omega t plus phi of R and plus complex conjugate. So you have two terms in D, in the operator D. You have two terms in the expression of E, and this makes too many terms because you have 4 terms, and we do not like 4 terms. It is much more too complicated. No, you do not agree? Okay, so in fact we will split the operator VEL in 2 parts, and we will call the first one the resonant one and the second one the non-resonant one, and we will very quickly drop the second one. And so the VAL is minus 1/2 of D times epsilon L of the operator. So this is the vector part, and then you have the EL of R. You have this term of internal degrees of freedoms, and you have the time dependence, which is minus E omega L t plus phi of R. Yes, I think it was phi L. No, I don't know. It doesn't matter. Plus Hermitian conjugate. Now there are operators, so they are not more complex conjugated, but Hermitian conjugated. So this is, the resonant part, and I call the non-resonant part the other one. So it is D times epsilon star of R and epsilon L of R. Yes, no, I keep it in the same direction. The only difference is there omega L t plus phi of R. So the only difference is in this sign, here and here. I have taken the same term with D, so it is this one which has the same coupling from the ground state to the excited state. And we will show that this sign is very, very important. And so, to make the notation simpler, we usually introduce the Rabi frequency, which depends on R, which is minus D epsilon of R EL of R. And so we just can write this as So this is the Rabi frequency. Okay, next step. Come back here. The next step is the rotating wave approximation. In short, RWA. And in the probably this afternoon in the lecture of York, you will see the RWE, which is totally different. This is the radial wave equation. So do not, this is not the same thing. This is the rotating wave approximation. Okay, so I have already said, in VAL, in the coupling, you have 4 terms, and 4 terms are too much. And so the natural question, and which appears in the splitting I made here, is what is the natural frequency for these 2 terms? And so I put quotes in natural in between. So it is the frequency at which the terms will evolve. So what we see is that the strange part in the expression I have written here is this operator. And this operator, as usual, it is simpler if you give a name to it. And so it is a raising operator, probably with a hat, because it is an operator. And if you look now in the Heisenberg picture, you look the time evolution of this operator, d over dt of s, and you know, I assume that you know, yes, no? It is given by the commutator between the atom, the operator you are interested in, and the operator. And if you put that here, you find that it is minus h bar omega 0 divided by a h bar s plus. And so, from this simple equation, you end up with the idea that your operator S plus evolves as an exponential plus I omega 0 t. And you are very happy because you see that, so if this one evolves as I omega 0 t, this one will evolve as only the difference in frequency. And so you have in VAL res, the frequency, the typical frequency is omega 0 minus omega L. And in V non-resonant, the frequency that appears are omega 0 plus omega L. Omega 0 from here plus omega L here. So it means that this one is a term that evolves slowly, because for the two-level approximation we have written that omega 0 is on the order of omega L, which means that this one, so it's almost 0, but this one is twice the laser frequency. So usually we write that this quantity is the detuning delta, and we will have, so the two-level approximation is valid if delta, absolute value, is much smaller than omega 0 and omega L. Then, in this case, you will have one term that evolves slowly and that will perturb a lot the Hamiltonian. One part that evolves slowly, quickly, and this one will average to 0. And so in this condition, then we can write that the VAL, the total VAL, is almost the VAL resonant. Only the resonant part will contribute. But it is an approximation too. And as Thierry pointed out, you have to track all the approximation you are doing, because otherwise at the end you do not know if your result is valid or not. And so for that I made the rotating wave approximation, and it is valid only if the detuning is much smaller than omega 0, omega L. But you also have a condition that is the Rabi frequency have to be also much smaller than the optical frequencies. This condition is usually always fulfilled in the optical domain. But if you play with microwaves, then in the microwave regime this condition can be not fulfilled. And so in some cases you have to be careful. Another case which is interesting is, for instance, if you just want to manipulate cesium atom or any alkali atom with a CO2 laser. It was, at one time, it was a very useful tool to make optical lattices. And in this case, you have the delta, which is on the order of the, yes, it is on the order of the optical frequency. And the two-level atoms is not a good model if you just play with an alkali and a CO2 laser. In such a case, you have all the levels that are involved in the mechanism, and you have to take them into account explicitly. Okay. In fact, yes, so we will see that later in the dressed atom picture. The basic idea is that So yes, in a few, just in a few words. When you have two atoms, two levels, and you put in between a coupling, then you shift the levels. And if this frequency, the coupling is too high, then the splitting is too large, and you are not anymore. This is the frequency here is omega 0, and if omega is larger than omega 0, then here the frequency becomes omega. Yes, yes, but it is for the average number of photon in the laser. No, no, no. You have simply you have two levels and you have a coupling. You have two springs. You have two springs, and you put a coupling between them, and the frequency, the resulting frequency for the oscillator you obtain by coupling two springs are split apart. And the problem is that if the coupling is stronger than the initial frequencies of the springs, it will dominate. And then the detuning that is defined as the atomic frequency minus the optical frequency has no meaning anymore, because it is the coupling that is the splitting. So this is usually I think we will see it in some way, but I'm not sure. For sure, in the dressed atom picture, it appears clearly. And yes, maybe we will do that also. Okay, so no, I had. So in the vacuum field is a mess, obviously, but you have the sum over all the mode of the vacuum field, and you have something like h bar omega of the mode times creation annihilation operator. So this is the number of atoms that are in the field. The vacuum field, no, for a mode, you have the which is proportional to something that is a dagger L plus AL. And once again, if you compute the atom vacuum field, you will have the usual 4 terms, because you have 2 terms here and you have 2 terms in D, and so you have 4 terms. And this is all. You will also, if you consider only the modes in the vacuum field that are coupled to the two-level atom that you are considering, then you can also here have the atom vacuum field, which reduces to the resonant part and which is proportional. You have always the sum over L, and you have a strange operator like that plus Hermitian conjugate. So it is rather ugly, but you can understand it, because this is the creation of a photon in the mode L. And to create a photon in the mode L, you have to, the atom has to go from the excited level to the ground level. So this is a resonant process where your atom loses its energy and the field gain the same or almost the same amount of energy. Any question? No? Okay. Now I think that I had the 1, so now I have a 2, and I will compute now the light force. And usually we put a S, but it is a light force. So I have already mentioned it at the very beginning, but I didn't explain it. So what is the semi-classical limit or description? And for the moment, I have introduced a position operator and a momentum operator for the external degrees of freedom of the atom. And we want to get rid of these operators because they are not very funny. And so we want a classical description of the atom, the position and momentum, pos and momentum of the atom. So it means that instead of having this operator, I will introduce a vector which is the average value of the position by definition. So, and momentum, which is by definition the average value on the so now the big question is, I know that my atom is a quantum object. It has an extension, it has a wave behavior, and so it has an uncertainty on the position and an uncertainty on the momentum. And how can I get rid of that to describe my atom just as a point particle at a given position and a given momentum? So this is the spread in space of the wave function, and I have a very simple hand-waving argument to say that if I want to be able to consider the atom that is just here and not there and somewhere else, I have the condition that the spread in real space should be smaller than some characteristic length in my problem. And what is the characteristic length in my problem? I have a laser field, so its characteristic length is the wavelength. So this is a simple part. This means that your atom, if you just by thought split it in two parts, the two parts have to see the same field, otherwise they will evolve differently and you will not be able to consider the atom as a whole. Now for delta P, we will make the same kind of reasoning. And if you just consider two parts of the atoms that have a different momentum, it means that it travels at different velocity. And if an atom has a velocity, and if you assume for simplicity that your laser field is just a traveling wave, then you will have some Doppler effect. And by Doppler effect, your different part of your atom will see a field with different frequencies. And if it is sensitive to this change in frequency, then you will not be able to consider the two parts of the atom as only one atom. So the condition is that the Doppler effect should be smaller than what the atom can feel, and what the atom feels is just the natural line width. If the apparent frequency differences are smaller than the natural width, then the atom will react the same with the different components. So it means that you will be able to treat the different parts as a whole. And so now I have the two conditions. So the Doppler effect is just simply KL delta P divided by M. So sorry, this is a delta. And so I have the condition. And now one more relation. We are in the quantum world, and so we have the Heisenberg relation. Uncertainty, which tells you that delta R, delta P is larger than h bar. And so we have a limit for delta R, we have a limit for delta P, and so we have to satisfy also a relation which is delta R is 1 over K, P is gamma M divided by K, gamma M divided by K, and so this quantity is so this part of the equation put together gives you a condition which is h bar squared K squared divided by 2m must be smaller than h bar gamma. So this is the recoil energy. You remember we had the recoil velocity, which was h bar K divided by m, and so if you just take 1/2 of m recoil velocity squared, you have the recoil energy. No, sorry, this 2 is not there, and so this is 2 times the recoil energy. Sorry. So this is known as the broadband condition. and it has to be fulfilled if you want to be able to make a semi-classical description of your system. If you have a line that is very, very narrow, and if the Doppler effect due to the absorption of a single photon brings your atom out of resonance, it means that this condition is not fulfilled. Obviously, you can do calculations, but not this one. And so I will not treat the case where we are not able to make the semi-classical description, so I will always stick to the broadband condition, which means that the line width is large enough, is much larger than the change in energy due to one recoil. Okay. Time is running very fast, but anyhow. So now I will consider timescales. In fact, I have a system which is composite. On one side, you have the atom with its internal degrees of freedom, and on the other side, you have the momentum and the position, which are external degrees of freedom that the atom just is moving. And so we just have to consider that we have an internal time, which is in fact the time needed to reach steady state for the internal degrees of freedom. And so, as we just have a two-level atom, and with a decay rate for the excited level, which is given by gamma, so this is the decay rate, then you can guess, as you have only one internal time, the internal time will be, so within a factor of 2 or 2 pi or something like that, but it will be gamma minus 1. Now we have, for the external degrees of freedom, so it is the same except that this is for external. Then, once again, we will consider the Doppler effect as a signature of what happens. And to define this external time, we will consider, so you have a momentum exchange. Which is, in fact, you exchange the momentum h bar k with a rate gamma, because you assume that you are almost saturating your transition. And so it means that the acceleration, your atom is something, so this is the velocity change and the rate change. And now, to get this external time, you will say that it is the time needed so that the velocity change gives you a Doppler effect. So this is the velocity change, and now I put a k in front of it. So this is the Doppler effect. This quantity has to be, once again, on the order of gamma. So this gives you the typical time scale for the change in momentum or in position. And if now you work out this, you find that the Tx is on the order of recoil energy divided by h bar minus 1. And if we come back to this condition, which was the broadband condition, the broadband condition implies that your external time is much larger than the internal time. And this is very nice, because it means that you will be able to perform a kind of adiabatic elimination. You will consider that your atom moves, but the internal degrees of freedom will relax very quickly, and so each time the atom moves, you will consider that the internal degrees of freedom are in the steady state. You are not interested, in fact, what occurs in the transient regime, which lasts a very short time in between. Okay, now I promise the light force. So before arriving to the light force, I need the force operator. So it is C and so once again we go in the Heisenberg picture, and we write again the operator. You know the result? So in fact here in H you have only the part coming from p squared over 2m that plays a role, and so here it turns out to be p divided by m, and here you have dp over dt, and here you have 1 over ph, and in fact the only part that doesn't commute with p is what depends on r, and what depends on r is just gradient of VAL minus gradient of VA vacuum. And by definition, this is the force operator. So this is the change of momentum due to the interaction with the laser field, and this one is the change of momentum due to the spontaneous emission, the coupling with the vacuum field. Okay, so this C was very short, because now what I am interested in is only the mean force, and we will restrict to an atom at rest. We know how to move it, so we just consider an atom at rest. And now, so it was there, but I will do the same thing as for the momentum and the position. I will replace the force, the force operator, by its mean value. And I will say that this is the classical mean force that is exerted on my atom. And this mean value is an average on everything that doesn't count. So it is the atomic state, the internal degrees of freedom, and obviously the vacuum state of the reservoir here. So now I just write the two components. Gradient of VAL gradient of VA vacuum. And now I will just use hand waving arguments and say that here you have the spontaneous emission that has the same probability in the plus k direction and in the minus k direction. So the average on the state, the vacuum state of this quantity, so the spontaneous emission is isotropic, so this one goes to 0 because you have the same probability to emit a photon like that or a photon like that. And I am happy because I have only one quantity to compute, which is the mean value of VAL. And I have 15 minutes left to do that, but I think we will manage. Okay. So, average on the internal degrees of freedom, and obviously I should have kept the VAL. So the VAL is only the VAL resonant, and it is h bar over 2 omega 1. Now it is just R, which is much simpler, and you have a j exponential I omega L t plus phi of R and plus CC, no, sorry, HC. Because you have still here internal operator JA. So I can easily compute the gradient because the only dependence on R are here and here. And so I can write immediately that the force operator is gradient of omega 1 divided by omega 1 times VAL minus a gradient of phi and all the rest that remains, omega 1 of r, e g exponential minus omega l t plus phi of r, and minus Hermitian conjugate. Because you have here the Hermitian conjugate, thus here you have a plus sign, and so you have a minus sign here. I have a minus here. Yes, probably. Yes. Gradient. Yes, up and plus. And so now I want to have the average of f, of the operator f, and I know that for any operator A, I have to compute the trace of A sigma, where sigma is the atomic matrix density. Or operator, it depends. Sometimes it is written rho instead of sigma, but usually it's always the same. And what is important is that the operator I have to deal with, which is this one, is just simply what we call GA, and by definition is J sigma E. And now, I have almost finished, I hope so, and I have the force, which is minus gradient of VAL, and which is minus h bar, so I have a gradient of omega 1 times sigma A, no, GA exponential minus E omega L T plus phi plus CC divided by 2, and the second term, which is omega 1 of R, gradient of phi, and sigma GE exponential minus E omega L T plus phi minus CC, and divided by 2. Is it okay? Yes? No? Okay. Now, at that point, we play some tricks. And I will introduce notations. And the quantities that are there are usually called U and V, and this quantity is just the real part of sigma JE of T and this one is the imaginary part of the same. So this is of R, obviously, but sometimes I forget it. And these are the first two components of the so-called Bloch vector. Nothing to do with Immanuel Bloch. This one was much older. This is Felix Bloch. And the last one, just to be complete, is 1/2 of sigma EE of t minus sigma GG of t. And so if I just want to rewrite the force with this new notation, I have a simpler form times u of t plus omega 1 of r gradient of phi of r times v of t. And I think I will stop here because the next step is just so it is the E and it is the optical Bloch equation and the calculation of the steady state, and I think that in 5 minutes it will not fit. So, and stopping in the middle is not a good idea, and so I think it is better to stop here and to finish the optical Bloch equation next lecture. Okay? Have you any question? Did you already know what I have told today? Most of you? Okay, so for the next time I will be shorter. Okay, no question? Thank you.